Okay, time to get started. I hope everybody had a good weekend. And back into it. So you may recall last time we were talking about, oh, by the way, quick thought while I'm thinking about it. Don't forget the attendance quiz, attendance code. Some of y'all just came in. Remember the clock's ticking. You got about a minute left on that. Okay, so we were talking about this idea. Let me scroll back. Oh, gosh. We were talking about this idea of can we locally, and that's the key word here, locally, given some curve, can I locally view, let's say, y as a function of x? And again, not globally, not everywhere. Obviously, this fails the vertical line test. But locally, we're only talking about this tiny little bit of curve right there. And locally, fine and dandy, no problem. Yes, y is a function of x. And again, why do we care about this? Well, sometimes when we have an equation given to us, right, sometimes with an equation like this, we want to be able to take derivatives. Right? Maybe I want to know the slope of the tangent line to this curve. Well, we don't have the function whose graph is this curve, and slope equals derivative is the calculus of graphs. It only applies to graphs, and this is not a graph. Right? So the idea that we could locally at least view y as being a function of x opens up the door to the possibility that maybe we might have some clever algebraic move, implicit differentiation that y'all probably all saw in high school calculus, would actually be legal and meaningful, right, as opposed to a bunch of nonsense. So again, at a point like this one, I don't care how locally you restrict your attention. There is no sense in which we can view y as a function of x. And therefore, not only does dy dx not exist, it's not even a meaningful concept. You can't take a derivative of something that isn't a function. Derivatives are something you do to functions. You can't take a derivative of a bicycle. The square peg round hole doesn't make any sense, right? So you can't even talk about dy dx in a case like that. Okay, so that's what we're interested in. And let's see here. Here is the punchline we talked through last time. The punchline is that problems, the kinds of things that would prevent you from being able to view y locally as a function of x, or where the curve, I like to say, wraps under itself. That's just a kind of a way I like to think about it, which of course corresponds to a vertical tangent line, which of course corresponds to a horizontal gradient, which of course would mean that the y partial of f is 0. Don't forget how we compute gradients. This gradient is just a vector of partials. Okay. All right. So all together then, let's do it like this. Problem would mean that the y partial is 0. That's what this says. Problem means that the y partial is 0. And then we write down the contrapositive. Y'all remember I've talked about the contrapositive a couple times. That's where you turn the implication around the other way, negate both sides, and it's an equivalent statement, right? The equivalent statement is that if you compute the y partial, if it's not 0, you know for sure there's no problem, nothing's wrapping under anything, and yes, you may view y locally as a function of x. So that's the big idea. This is our first example of the implicit function theorem. My little thing keeps sliding around. And here's a three-dimensional version. Now this is same idea. By the way, everything we did up to this point could, arguably should, different schools of thought, could have at least been made in a single variable calculus class. Right? We'd have to finesse this idea of how to talk about gradients and okay, fine. But this is addressing what we're eventually going to view y locally as a single variable function. And when you've done implicit differentiation back in high school or wherever, it was examples like this, right? So now we're really, for the first time, extending this up to a context that wouldn't have made any sense at all in high school, right? But the same basic idea applies. If you have a point, let's say like about right there, right? And if I say, is z a function of x and y? Well, okay, not really, but look, if locally, if I just look nearby, just in the vicinity of that point, forget about stuff down here, right? We just locally, right? Yeah, at a point like this, yeah, right? You can, right? Y, z is locally a function of x and y. But it doesn't work everywhere, and again, I think you can probably see this coming. Where it fails is at a point, oh gosh, I want to be in the pencil mode, at a point like this point right there. That's where the surface, I should have had a piece of paper prepared here. That's where the surface is in the process of wrapping under itself. And notice, it doesn't even really matter whether it's like this or like that, right? The sort of horizontally, which way is this kind of it pointed, doesn't matter. The question, the problem with viewing z locally as a function is whether it's vertically doing this. And how it's turned, who cares, whatever. And so the idea then is wrapping under corresponds to a vertical tangent plane. Vertical tangent plane. And again, vertical tangent plane means horizontal gradient, which of course, again, think about how we compute gradients. Made up of a bunch of partials. Horizontal would mean the z partial is 0. How we doing? Is everybody following along? Is everybody happy? As happy as you can be on a rainy Monday morning in a math class? Okay. So, what you may have noticed, and this pattern is right, whichever variable you want to be able to view locally as a function, that's the variable whose partial arbitrates the question. Right, in this first example, we were looking at a level set. I wanted to know if I could view y locally as being a function. Okay, well, I need the y partial of course, the function whose level set I'm looking at to be non-zero. And then down here, the question was, can I view z locally as a function? And that question, again, I didn't write down the contrapositive sort of punchline, but again, it's arbitrated by the z partial. So that pattern continues. Now, this is not a class about proofs and rigor and stuff like that, so I'm not going to go through a rigorous proof of this. It wouldn't be appropriate, but I do think that you can persuade yourself of this. If you're not already persuaded by the two examples I've shown you, right? Ask yourself the question, how would you decide in a case like this, how would you decide if you can view x locally as a function of y? And you draw the picture and think about that and make the kind of rip off this argument, but everything's going to be sort of turned sideways, and just think through the details, and you would find it's the x partial that matters. And then likewise, in a case like this, what if you want to view x as a function of y and z? Or what if you want to view y as a function of x and z? Now the picture is a little harder to draw, right? But the answer ends up being analogous, and this pattern continues. Whichever variable you want to view as a function locally, that's the one that you need to take the partial with respect to. Is that everybody buying what I'm selling here? Okay. All right. Good exercises. I encourage you to do that. Okay, so that's the theorem. Right now, there's a regularity issue. I do need the function. Oh gosh, look at this typo. I'm sorry. No one's ever pointed this out to me before. This needs to be a capital F, of course. Sorry about that. Several years worth of students have not pointed that out. So, anyway, I'm not above typos. Right? If you see something that doesn't make any sense, you're very encouraged. I appreciate pointing out my whoopsies. Okay, so the function whose level set you're looking at, that function does have to be C1, so there's a regularity issue there. All right, fine, sort of, math, formal stuff. And notice the pattern continues. Whichever variable you want to view locally as a function, you take the partial with respect to that variable. That's all the implicit function theorem says. Take the appropriate partial. If it's non-zero, no problem. Okay, let's do one. Okay, here's an equation. Now, I will point out in this example here, I did do something nice. Life will not be this nice, and I will not always be this nice. Right? But I went ahead and I wrote the equation as a level set. Right? Now, that's very, very important. It's got to be a level set. If you go back up here and look at the argument, it's only because we're looking at a level set that I can make statements about which direction the gradient points in comparison to the curve or surface, right? So you've got to rewrite your algebra, and again, here it is again. It's got to be as a level set of whatever, of some function. That's the function you need to identify. Right? So this came pre-formatted correctly, and you can't count on that. You always have to be on the lookout for that, so heads up. Anyway, that's nice. So let's see here. So here's the function whose level set we're looking at. And here we go. We want to know if x can be viewed locally as a function. Okie dokie. Well, then we're going to take a partial with respect to x. Again, partial of the function whose level set we're looking at. Everybody see that? Any questions? Everybody good to go so far? Okay, and then, plug and chug. Okay, so we have to we have to compute that partial, easy partial. Of course, now we're interested in what's happening near a particular point, right? I want to know about this point 1, 2, 3. We already know the point matters. Different points, where the surface or curve may or may not wrap under itself depends on what point you're looking at. So you got to plug in the point in question. And what we get then is that the relevant partial is non-zero. And not zero means no problem. Yeah.
Why do you say near 1, 2, 3 when 1, 2, 3 is on the surface?
Yeah, that's okay. Absolutely, great question. So let me go back to the picture here. So when we talk about whether something can, wrong mode, whether something can be viewed locally as a function, so we're talking about in a neighborhood of that point. And so if you're literally at a single point, that's not a graph of anything, right? So you kind of need a little bit of curve on either side of it. Yeah, right. Good question. Okay, right. So, simple question, straight answer. And at this point, you're welcome to view x as being a function. You can talk now. It would make sense now that we know x is locally a function. We can talk about how to take a derivative of it. I can talk about the partial derivative of x, for example, with respect to z or y. Take a pick. Is that cool? Okay. Until before we had established that x was locally a function, if I had just looked at, this, if I had just looked at this equation and said, hey, what's the partial of x with respect to y? What are you talking about? X is an input variable. I mean, zero? Is it because x is an independent variable. It's treated as a constant when you take the partial with respect to. The intention of the question that follows here doesn't make any sense until you establish that x is actually a function. Okay. All right. Now that we know x is a function, how do we take derivatives of it? And I'm going to show you two different approaches how to answer this question. Well, I'm going to wave my hands at this one. I'm not actually going to talk through this. This is the closest thing I'm going to show you to a right and proper way to answer this question. The bad news about the right and proper way to do it is you can see it gets a little hairy. And it's doable, but I don't think we need to wade into this. Anyone who wants to ask me about this in office hours, love to, right? Come on in, we'll talk about it. It's ultimately no big deal. I'm going to show you the kind of quick and dirty hack, sort of math crime, but nobody gets hurt kind of deal. Sort of, this is how you can do it much more effectively and conveniently. So let me talk you through what's going on with this picture. Keep in mind the given is that f is a function of various x variables. Right? Keep in mind that we have a test now for identifying when one of those variables can be viewed can be viewed as a function of the others. And if xi, for example, is a function of the others, then I can reasonably ask, how would I take partials of it? Let's say, how would I take its partial with respect to xj? And keep in mind, if you're going to take the partial with respect to xj, that means all of the other variables are to be treated as constants. Right? So everything in gray, I like to use gray for things that are constant. So xi is a function of all these other variables with the understanding that f, keep in mind where all this came from, f is a constant. We're looking at a level set of f. Right, so let me go ahead and add on here explicitly, this f is constant. Right? In fact, let me color that in gray too, just to emphasize, f is constant. And so the question then is, how would I compute this derivative, partial of xi with respect to xj, with the understanding that insisting that f stay constant effectively allows me to treat xi as a function of these other variables, including xj. Does everybody see the context? Did I see I thought out of the corner of my eye? No? Yes?
I was just wondering, why do you call it a derivative of a new function?
Yes.
It doesn't feel like we can define this new function, right? What exactly would you call it?
I mean, that's a good question. I suppose we could give it a name. We tend not to do that because when we talk about taking derivatives of it, we just tend to use this sort of fractional Leibniz-like notation where we don't need to name the functions. We talk about the output variable and the input variable. So we just kind of don't need to give it you can call it a name if you want to.
But we have nothing to write it as. It's just like S at
this
point.
Yeah, I could. You're asking questions that will get us into this discussion, and so all good questions. But I think we don't want to go there. But if you do want to go there, let's talk after class. I'm happy to do it. Right. Okay. So f is not allowed to change. That makes xi a function of all the other variables. I want to take the partial with respect to xj, which makes all these other variables also constant. And now, here's how easy the question becomes. If I were to take the overall partial of f, which keep in mind, it's not allowed to change, it's constant, with respect to xj, overall partial. Well, I know that overall partial is 0 because, again, f can't change. Right? I know that's going to add up to 0. And then I just have to write down the two different paths. And here they are. There's that path, which gives this term. And there's this path, which gives this term. And by the way, I fully recognize I'm breaking my own rule, right? This totally violates the rule about compositions and inputs and outputs. And this diagram does not pass muster, right? This is a great violation of the rules that I made a big deal about, talking about the chain rule. And again, math crime, that works out fine. And if you want to fix it, this is how you fix it. And again, I trust me, it's fine. I think we're going to all be better off if we just kind of go with this. Is that cool with everybody? And again, anybody who wants to see the fuller, proper discussion, come on into office hours. Let's do it. Okay. But computationally, this is much easier. And then you notice that the thing we're trying to compute is right there, and then you just solve for it, and we win. And there's our formula. It's a really nice little formula. Let me sort of get rid of all the mess. That partial derivative is computed by... I missed. Oh my gosh. computed by that formula right there. Yes?
Where's the negative come from?
Yeah, it comes from literally, if you solve for this, that's right, this is what we want to know, and when you solve for it, you have to move this term to the other side, and yeah. But that's a great segue into the next thing I want to talk about, which is that negative seems kind of wrong, doesn't it? I mean, after all, can't I cancel the partial f's? You see the temptation, right? And if you cancel those, then the denominator of the denominator, shouldn't that be the numerator? And let's see here, the denominator of the numerator, shouldn't that be the denominator? It kind of feels like this would work without the minus sign, doesn't it? Y'all see the temptation there? This is a siren song of nonsense. Absolute nonsense. And again, I made a big deal a long time ago when we were talking about the chain rule that, you can't treat these things like they're independently meaningful and do cancellations, right? So what we're seeing here is yet another case of, you can't cancel those things, right? It will get you into trouble. But what gives? I mean, this seems wrong. This minus sign seems really wrong. And here's the way I like to think about it. Let's look at these two terms. I mean, ultimately, this minus sign stems from the fact that these two terms both have positive coefficients here, right? The little algebra solve. The minus sign comes ultimately from this plus sign. So why do we have a plus sign here? And the idea is that these two contributions are not equal. They're not supposed to be equal. They're supposed to be opposite. They're supposed to cancel because f can't change. Right? These two different contributions have to cancel each other. They have to be opposites. To recognize the fact that, again, f is not allowed to change. We're looking at a level set of f. F is constant. Does that make sense? So that's why we have a plus here, and therefore that's why we have a minus here. Okay. All right. Now, that said, let's talk about test strategy here for just a minute. You see this minus sign. This is the minus sign I'm talking about here when I say this is very important. The reason it's important is that if you forget this minus sign, I'm just telling you what it looks like. When you write it down without that minus sign, it makes it look like you believe in the cancellation. Right? It makes it look like you don't understand that these terms are not equal. These terms are opposite. Right? That's really important to fundamentally what is actually happening here. So that minus sign distinguishes a perfectly valid equation from nonsense, fake cancellations that don't work and don't mean anything. This minus sign is what distinguishes valid from garbage. And it's just tremendously important as a result when it comes to exam grading. Does everybody see that? So make sure, I don't know what personal procedures you might have, right, to make sure that you do not forget something, but whatever you can do to make sure you don't forget this, do it. It's a really big deal. Is everybody following? Okay. Make super sure you don't forget that minus sign. Okay, so let's do one. You will notice that we're looking at the same surface that we did previously. And we have already established in that previous example, we already know that x is locally a function of y and z. So we already know that this is a reasonable question. Now again, if we had not already established that x was a function, you want to go around taking derivatives of things that we don't even know if they're functions? That doesn't make any sense. I don't know what that means. Again, you cannot take a derivative of a bicycle. Right? So, thankfully, we have already established that x is locally a function of y and z, and thus this question is perfectly reasonable. So that said, then what is the answer to this reasonable question? How are we going to compute this partial derivative? So we have a formula back here. Now you'll already probably have noticed the problem. Here I set things up where the inputs, capital F, were variables called x1 through xn. And in such a case, this is how the formula works. Here the variables just aren't called x1 through xn. So, oh my gosh, are we going to have to write down a whole new diagram and go through the whole process again? No, you don't. You don't have to go through that whole process again. I'm going to tell you how I do this. I think this is a perfectly reasonable way to go. First, write down that minus sign. Don't forget that. Make sure you don't blow that. Write that minus sign down first. Right? So, write that down first. And then remember, other than this minus sign, yeah, it's as if they're fractions. It's as if the cancellation works. And so, garbage nonsense though it is also kind of a nice memory tool. Right? So I use the fake nonsense cancellation. I use that as a memory tool. And so, for example, here, I want to take the partial of x. So that must be in the denominator of my denominator. I want to take the partial with respect to z. So that must be in the denominator of my numerator. And the thing that I'm looking at a level set of, right, the thing whose level set I'm looking at, that's the thing that I compute those partials of. Is that cool? Now, again, I feel a little bad about taking something that's really, really wrong and then kind of making use of it, but it serves very nicely as a sort of a way to get the formula on the page. Okay. And then it's all over with the shouting. You got to compute the various partials. You got to plug in the point in question. Again, we're looking at the point 1, 2, 3, and you plug that in, arithmetic, and answer. Everybody good? All right. Okay, so last a warning, and now I just want to emphasize this is kind of the second. Well, I'll call it the second sort of like opportunity, to have a problem. Right, the second biggest problem that I see when students work questions like this. A lot of students will look at a question that won't come in two parts like this one did. This one came where it explicitly asks first, can we view x as a function? It explicitly asks that and then subsequently says, since that's been established, now second question, what is this partial? Usually it won't be like that. Usually you will not have already established that the thing the question is asking you about the derivative of is already established as a function. It just usually won't be given. I mean, how it tends to come up in practice is you've got some equation and some point on that surface, and the question will come up, hey, I sure wish I knew what this partial derivative was. And what you have to remember is it is your responsibility to establish first that the thing you want to take a derivative of is actually a function. You have to establish that first. It's a big deal mathematically, right? You got to establish first that it is actually a function, and only after you do that can you secondly, compute with the formula. So I emphasize. Whoops, where is my? Okay, I emphasize here. Checking that the thing you want to take a partial of is actually a function is usually about half the points in a problem like this. So just FYI, it's about half of the work. It's about half of the concept. So it's about half the points, ballpark, plus or minus. So make sure not to forget that also. Does that make sense to everybody? Any questions about policy on this? Okay, so make sure to do both parts. So you would have to first do this, and then subsequently do this. Okay, moving along. Off to chapter 3. Now, we've already done 3.1. Remember, I like to do 3.1 a little early. I like the ideas of 3.1 as a tool for talking about the chain rule, right? We talked about the chain rule as a discussion about how you relate velocities of various curves, which is what 3.1 is about. So on to 3.2. There's kind of a couple of parts to 3.2. What's most important to me is this part right here. Right, so we're going to focus on this. The rest of 3.2 is cool math. That's a digression from where we're going, and as cool as it is, and as much as I like it, we kind of don't have time to focus on it. It's ultimately not such a big deal. But let's talk about this now. So we've already discussed this idea of a parametric curve. Position's a function of time. And we've talked about how you can take the velocity vector. So the velocity vector, r prime, so the derivative is the velocity vector for one thing. Right? And the velocity vector would be some non-unit vector in the great majority of cases. Let's say something like that. Here's your velocity vector. A really important object that we're going to need to talk about is what I'm going to call the position differential, dr. I don't think we've introduced this yet on a parametric curve, but this is a really important idea. Keep in mind what d means. D just means differential. Differential means linear approximation of how much that thing changed. So when I write dr, we're looking at this r thing, and d says how much has that r changed. And if you think about it, r gives you your position. So this means what is the linear approximation to how much position has changed. And well, it's going to be something like this. And you can think about this a couple of different ways. On the one hand, over some differential amount of time, you actually moved something like this. You were here, now you're here. I mean, you're on this green curve after all. Right? But the linear approximations don't account for curvature. Right? So the linear approximation would be based on how you're moving when you're at the point, and so you'd be off a little bit. Right? Another way to think about it, of course, this is in fact single variable calculus. T is the only actual input variable, and so this is really just kind of an immediate recopy for the single variable. dr is r prime dt. And algebraically, I think that's very simple. All right. Okay. So there's another couple of observations to make. Let's see here. So let's talk about ds. ds just says how long is that piece of curve, or more to the point, what is our linear approximation to how long is that piece of curve? And I'm going to make the observation that it's our best approximation of how long that little green piece of curve is would be, well, what's the magnitude of that dr vector? That's the dr vector. It literally is representing our estimate of how much we've moved. Where we started to where we've ended. The magnitude then would be our estimate of the distance. So that's that idea. Is that cool? Right. And of course, you can take, you can take the formula for dr that we have here and take its magnitude, and that gives that one. Okay. All right, last thing I want to point out is there's a really useful vector to talk about, very important. Let me just clean up my mess here. And that is the unit tangent vector, like this. Now, we've got 3 different tangent vectors to keep track of. This does get a little confusing, so you've got to make the conscious effort to take the time to not let these ideas conflate in your mind. We're not talking about the velocity vector. Right? The velocity vector is this, physically relatable. I mean, it's speed and direction all accounted for. And we're not talking about the DR, the position differential, right? We're talking about the unit vector that points in the direction that the curve is going. And of course, now it's easy to write down a formula for it. The velocity is a tangent vector. If you want a unit vector in that direction, divide by its own magnitude, of course. Nothing to it. And with that noted, let's see here. With that recognized, I claim that T ds, this product, TDS, is our dr vector. That's the claim that I'm going to make here. It's this this vector here like that. And why would that be? And there's a couple different ways you can see this. I think the most immediate and satisfying way to see it is, let's just think about, well, what is dr supposed to be? Dr is supposed to be a vector that points tangent to the curve. Okay, well, this t factor ensures that this is pointing in the direction that dr is supposed to point. Next question, wait a minute, what's the magnitude of dr supposed to be? The magnitude of dr, we've already talked about, is ds. Well, this ds makes the magnitude of this expression what it's supposed to be. Right? So, how do I know that this is dr? Well, these two expressions, dr and TDS, they point in the same direction and they have the same magnitude. That means they're the same vector. Everybody buy it? All right. Now, of course, another thing you could do is, let's see here if I can, so you could say, well, T is computed by that formula, and DS is computed by this formula, and this times that gives you VDT, which is dr. That's algebraic and ultimately a little bit less satisfying, a little bit less intuitive. But if you want to see algebra work it out, you can just plug those formulas in and it works out. Okay, so that's the most important thing that we're going to do in section 3.2. The rest of it I'm going to go through a little bit quickly because it's ultimately just kind of an idea we aren't going to be using very much, and it's computational. But this stuff here is really important. Now, it's going to show up most dramatically when we get into chapter 6. So it's going to be a while before we get to it. But once we get to chapter 6, this is going to be a really big deal. Okay. All right. So real quick, let's go through the rest of this stuff. Suppose I want to compute the length of a parametric curve. How would I compute the entire length of a parametric curve? Well, look, how about this? How about we break it up into little pieces? And on each little piece, I can compute ds. By the way, we have our little formula for ds right there. Here it is. ds is magnitude of velocity times dt. And if you want to add that up over the entire curve, okay, go ahead. That's what an integral is. Right, so nice little convenient formula for how to compute the length of a parametric curve. This integral, it's an integral of the speed, basically. Which I think is pretty believable. Here's an example. This is very plug and chug. You'll notice that the position vector I'm given, right? All I do is I take that position vector, I compute the corresponding velocity, and as per this formula, I do an integral of the magnitude of the velocity. It's just plug and chug. And that said, notice the integral, it's a nasty integral, and that's why I stopped right here. Right, it's going to be a real pain. I'm not even sure. I haven't worked out whether this is even a feasible integral to, realistically, to be able to compute. But anyway, that's how one would do it. And by the way, these integrals do tend to be ugly because you can even just see right here in the form of the integral, there's a magnitude. Magnitudes are square roots, and square roots in integrals tend to be hard. Right? So majority of these are hard. Okay. All right, so why would we care about such a thing aside from, well, sometimes you want to know how long something is, I suppose. There is a nice idea called parametrizing by arc length. First, let me show you what I mean by reparametrizing. This is ultimately a pretty straightforward idea. Here's a curve, and y'all remember the graph parameterization, I hope, right? Going back to chapter 1, somewhere early chapter 1 as I recall. Let t be the input variable, right? So x is equal to t. That means y has to be t squared. Graph parameterization. And now let me just observe. Here's another perfectly valid parameterization. And if you don't believe me, just note that these formulas for x and y work in this equation. Let's plug them in it. Sure enough, it works. So that's a different, perfectly valid parameterization. Is that cool? Everybody see how that? Just another way to go. It's kind of a weird choice, but it technically works. Well, another way you could think about this is that I took some relationship like this between my two parameters, my original parameter t, my new parameter q, and if you just plug this formula for t, plug that into there, notice that's how you get this new parameterization. So this is called reparametrizing, and anytime you can write your parameter in terms of some other parameter, you can plug it in. Right, that's all it is, just plugging in. Not that weird of an idea. So the clever observation is to point out that when you have a parametric curve, and if it's parametrized with respect to time, let me tell you what my new parameter is going to be. My new parameter, I can choose any parameter I want, right? My new parameter is going to be distance. We'll pick some arbitrary starting point, t equals 0 makes sense. I mean, why not? It seems like a natural choice, right? Whatever. But at any given time t, I look at where I am at that time t and ask, okay, well, what's the total amount of distance that I've covered since time 0? That distance is a function of t, so I have an algebraic relationship. And if you just plug in that formula, then you reparameterize into the parameterization, and you get that same curve as a function of s instead of as a function of t that it was before. So now, why would we ever do such a thing? What's the advantage to having an arc length parameterization? And it turns out that algebraically, it's kind of cool sometimes. Sometimes certain proofs that you might want to do, which we're not going to do. Certain proofs make a lot more sense with an arc length parameterization. Right? So it can be a very useful thing. And I like to point out it's intrinsic to the curve. I think this is a good one to sort of talk through. It is, I'm going to say now, I like that word natural. Let me give you my favorite example of how you can think of this as being natural. Think about a road trip that you might be on. Right? We're going to go from Duke campus to, I don't know, New York, whatever. We're going to take whatever road that is that takes us there. Right? We could talk about our position, keep track, talk about our position as a function of time. Right? You just keep track. Oh, where was I at 11 o'clock? Okay, you write it down. Where was I at 12 o'clock? And you write that down. You are literally effectively viewing your path that you're driving as being position as a function of time. Your act of driving over the road is a parameterization of the road. Okay, all right, so there's that. But that's not intrinsic to the road, right? That depends on how I drive. If I drive faster, it's a different parameterization than if I drive slower. Okay. The arc length parameterization would be the mile markers, right? where am I when I'm 15 miles out of Durham? Well, there's a mile marker right there. That's where 15 miles outside of Durham is that spot, and they put a marker there, right? And then 28 miles outside of Durham, they put a mile marker there, right? Does everybody know what I'm talking about with the mile markers? And the mile markers, you'll notice, are intrinsic to the road. They were there before it even occurred to me to take a road trip, right? So it is literally intrinsic to the curve, and that's a cool thing. That makes it natural, makes it meaningful, right? It's not about me; it's about the road itself. And so, anyway, try to make sure to understand this distinction between the road and the road trip, right? That explains the difference in what we're talking about here. Yes.
How do you say that? Like the up part. How does S get into R?
Yeah, well, so I mean, this algebra here will allow me. I mean, I got to compute an integral, and it's a pain and everything, but I can solve for S as a function of t, and then you have to invert that. You have to solve for t as a function of S. That would just be within the algebra, and if you can solve for t as a function of S, then you literally just plug it in, like we did here. If t is a function of your new parameter, then you just stick it on in there. Yep. All right. So here's an example. And by the way, I crafted an example here that is, I'm not going to say it's the easiest possible, but there's very, very few examples of this that are neither impractical or boring, right? So there are easy examples where we're moving at a constant speed. Right, straight line, constant speed, and this will all work out great, but it's also pretty boring. And there's many examples where the algebra is just intractable. So there's a million of those as well. And finding ones that you can actually do and that aren't sort of trivial is a very narrow thing. So I just want to show you how hard it is. I've gone to some trouble to craft this example where position, you take a derivative that gives you a velocity that when you compute the magnitude of it, the square root goes away. Give me 2 seconds. So it's a little bit of a trick shot, by the way, to craft. It's doable, right? Craft an example where the derivative, right? You see this term turns that minus into a plus that makes it a perfect square. That makes the square root go away. It's clever, right? And even still, even having crafted one that's like algebraically very, very fortunate, now I got to solve for t in a cubic equation, and that's kind of impractical. So that's unfortunate. Yeah, you had a question.
I was wondering, the uppercase t is not what you're referring to the unit vector before. This is just you already use lowercase t, so you're using
I'm not talking about capital T at all here.
Okay.
Yeah, that's right. This is little t only, and it's representing time. That's right. Yeah. Okay, so algebraically these tend to be a little impractical. I think there's at least one homework exercise where you're going to do something like this, and the textbook author, has gone to the trouble of finding a very cleverly crafted function where not only does the integral work out nicely, but it's also something where you can solve for t as you need to. So it will work out. So, anyway, be careful with that. Okay, we got a couple minutes left. I do want to make a little headway on section 3.3. We're going to introduce a new object here called a vector field. It's a new kind of a algebraic / geometric / physical critter, and it's going to be something that we're going to study intensely in chapters 6 and 7. Right. So this is another sort of preview of things to come. So this new object is called a vector field. The idea of a vector field is that whatever point you might be looking at, and you think of that point as being an element of the domain Rn, at every point we need to have a vector, and that, what we call the field vector, that's the output. You think of that as a vector, also in, of course, Rn. So this is the big idea. We write a vector field as a function, But, I mean, morally, I mean, the way you think about it, the way we're going to use it in practice is this idea that at every point there is an associated vector, and the way we draw the picture is the field vector you draw with its tail at the point where it was evaluated. Now keep in mind, the field vector, it's a vector. You can draw it anywhere, but to draw a vector field, the tail should be at the point where it's evaluated. And you get a bunch of pictures like this, and turns out these kinds of pictures are fantastic models of all sorts of physical stuff. And you could probably even sort of see it coming. Tell me if this doesn't conjure to you the idea of a fluid flowing. Right? You could imagine, for example, this one over here on the left, maybe this is like ocean currents, and wherever you might happen to be, well, the current is going in some direction. In a different place, maybe it's going a different direction. Vector field is the perfect model for something like ocean currents. You could imagine air currents, and maybe here there's an updraft, or maybe this is representing the flow of birds. I like the bird metaphor. There was a bunch of birds on the ground, and somebody said boo, and the birds all fly straight into the air, but in different directions. Well, you're going to have a vector field describing the flow of birds. Does that make sense? So we're out of time, but we will pick up and talk more about vector fields next time. See y'all later.